Welcome to the last Elmer webinar for this year, which will be given by my colleague Peter Robak. It's the last in a series of 3 this winter, and also a continuation of the webinars that have been starting actually last spring. Some practical guidelines. If you have a question, please write it into the Q&A field of Zoom. We try to address everything either by written answer or by giving you a possibility to speak and then ask your question. The chat may be, of course, used for general discussion. The presentation slides, as always, will be available after about 1 week, so with a 1-week delay under the Nick Funet place you see here on the screen. And as an information, this webinar is being recorded naturally as we put it on YouTube afterwards. Here is a list of the previous webinars, all of them to be found on the YouTube channel. So if you missed one and are interested, you can use the opportunity to go through them online via the YouTube channel. And I guess without any further ado, I will give the screen to share them to Peter Robak and shortly introduce then the topic of today. So it's about multiphysics simulations with Elmer, the very core topic of Elmer. Examples on how to weakly or strongly couple different models within Elmer. Peter, take it away, please.
Thanks, Thomas. Okay, so as said, yes, we will talk about multiphysics simulation with Elmer, which is in the heart and soul of Elmer. And there are many ways to classify the problems when you are talking about coupled problems. So you can do weak or strong, have weak or strong problems, and you can maybe use loose or tight coupling schemes for those. You can model problems or present them at least on a continuous and discrete level. So this is mainly a matter of taste, because in the end, at least in finite elements, you end up with the discrete implementation, but you may present it as a continuous presentation, and that may affect sort of some of the implementation issues. You can couple on the bulk, so on the highest dimension, or you can couple on the boundary. You can have same or different mesh. You can have implicit or explicit coupling. So implicit would mean that the equation or the coupling does not appear directly, but it's sort of indirectly via some material law, for instance. Whereas in explicit coupling, you see for instance, the source term directly. You can have same or different scales, and this will also be addressed here. And you can have the same method for the different problems or different methods. Sometimes this is, you can call it hybrid methods, or then you can call heterogeneous versus homogeneous methods. So there are many different sort of aspects how to classify these. And I try to give some examples that illuminate these different words. As a first example, I take this nice case that we also have in Elmer tutorials. So this is a case where the flow and the heat equations couple. And this is a relatively simple geometry, and the equations are well known. We have a hot inflow coming in, and then it's cooled in this pipe. And if we assume that the material properties are constant, then this is a hierarchical problem. So we first solve for the flow and then for the temperature. So here is the way how the hierarchical coupling is done. So we just make sure that we first compute the Navier-Stokes equation and then compute the heat equation. And if you look at the command file, then you see that, okay, my viscosity is defined to be a constant, and I only take one steady state max iteration, which defines how many iterations you take on the coupled system level. Now, you can have easily coupling through some material law. So let's assume that we have a temperature-dependent material law. Here, the temperature-dependent viscosity. I think this is by Thomas, so nice example. So you can, in Elmer, express the temperature-dependent viscosity in many different ways. So you can have a table, Matsi, Lua, or a Fortran routine. So we need to add this. So this functional dependency, in this case, we use it as a Fortran routine, and we also need to add some coupled system iterations. So the differences of these two would be that here in the hierarchical, we just solve once and have constant material properties, and here we need to iterate over the coupled system level. And if you look at the command file, then what changes is that we need to give the viscosity as a function. So here is the simple function for water viscosity. So this computes the water viscosity, and then we need to add some steady state iterations so that we can solve this coupled system. And in this case, it's very easy. So this converges very, very quickly. And the effect of viscosity is barely seen. So just a few iterations are needed. And why is it so? I think you can explain it by the driving force is the forced convection. So you have some forced inlet profile coming in, and this is not affected much, even though the viscosity changes. So the forced convection is almost the same, even when you have a little bit different viscosity profile here. So in this kind of case, of course, weak coupling works like a charm. So this is a nice schematics by Thomas, how the different iteration levels are nested. So we have a innermost iteration level if we are using a iterative method for the linear system. Then we may have for each equation or each module, we may have additionally nonlinear system iterations. And if these are coupled, then we can have steady state iteration, which basically in transient problem means that we have a steady state iteration within time step. So we can choose to have, if we have time dependent systems, we can choose to have one or several iterations on the coupled system level. So do we want to have a fully convergent coupled system or not? Sometimes it's actually even more accurate to take, for the same cost, computation cost, take smaller time steps and just use one steady state iteration. So here is a more stronger coupling. So this is a case of natural convection. So the equations are quite the same. Now we have a temperature dependent density. So this is linearly depends on the temperature difference. And now this is much, much more difficult to solve because the driving force is actually caused by the temperature dependent density. So you don't have a sort of additional external forcing, but you really are dependent on the solution of the heat equation. So you need to solve typically at least a few times within time step if you want to have a convergent solution. And in this kind of case, the numerical coupling is usually okay. So if you decrease the time steps, it helps to stabilize the iteration. So these kind of cases are typically conditionally stable. So if you if you shorten the time step, you can eventually find a time step that will give you a convergent solution. And actually, if you have a longer time step, there isn't even a solution with a stationary solution with high enough temperature difference. So there are test cases in the test suite starting by natural convection if you are interested in these kind of cases. You can also have even stronger coupling. So one field of problems that we have studied is acoustics, where you have sometimes you need to model the equations in harmonics. So you basically make a time harmonic ansatz, and you get a little bit different equations, but nevertheless they are the origin of the equations is the same. So you have a momentum equation, an energy equation, a continuity equation. And when trying to solve these kind of equations coupled, it turns out to be very difficult to get the sort of convergence with loose coupling. So we actually need monolithic matrices for this kind of problem. And actually for these equations, there is this acoustics solver in Elmer, which builds all these equations as a coupled system. So the downside of this is that the actually resulting matrix is very, very difficult to solve. So you can maybe find a solution using direct solvers, but eventually if you want to have solve bigger problems, you end into problems. And the remedy for that Mika in our group found was to apply block preconditioning techniques for this. So you basically make the problem to be a little bit different, and it's then described by this block system where you then can precondition it with this by the lower block diagonal. So the problem is then further moved to finding optimal solutions for these different subproblems. And these principles were later applied to Stokes' equation, which is monolithic in its own right. So you often have the sort of trouble that if you want to have a monolithic linear system, then you end up having problems in solving that because it may be very ill-conditioned, or you may need to use a lot of iterations for that. So to sort of give a little bit more insight, I generated a sort of simple prototype problem. So I assumed that you would have problems associated with F and G, and you would try to find a solution for these two equations. F with variables X and Y would be 0, and the same with G. So the main algorithms would be the hierarchical coupling would be, of course, that you first solve the one and continue to the next one. In loose coupling, you go from one to the following and iterate until you are converged, or in tight coupling, you try to solve both at the same time. And how to do the tight coupling? So when you apply Newton's method for this kind of coupled system, then you end up having something like this. So what is noteworthy that this, of course, is probably never formed in this way, but when you have a coupled system, then these cross terms may become quite difficult to estimate. And but formally, this would be the way to solve tight coupled problems. And to solve loosely coupled problems, we would apply these equations one by one. And actually, mathematicians can show that this kind of loose coupling can be shown to converge if these matrices fulfill this criterion. So basically, what this means that these sort of diagonal matrices, they should be dominant compared to the sort of coupling matrices. And of course, this makes a lot of sense. When you decrease the time step, what you introduce the maze matrix, a bigger and bigger maze matrix, which means that you end up increasing these diagonal blocks, and therefore the sort of system becomes more stable. So that's what is meant by the sort of conditional stability. Okay, let's go to a second class of problems. So we can do fluid structure interaction in Elmer, and there are different ways to do it. So, of course, the natural way to do is to do this hierarchical coupling. So you first solve for the fluid flow, and then estimate how much forces it affects on the structure, and then compute the structural sort of displacements. And if the structure is rigid, then you actually just may need one iteration. If the structure is sort of more flexible, then you need to iterate, and iteration method quite often works quite nicely. In Elmer, you have two ways to setting the boundary conditions. You can use the sort of a built-in, sort of coded-in condition FSI-BC, which means that the Navier-Stokes equation knows how to deal with the stress solver sort of internally, or you can use the library functionality to sort of compute the discrete reaction forces, and then have the sort of forces, nodal forces, be exactly the sort of reaction forces of the other equation, or actually in this case opposite to the reaction forces. So you have these two different methods, and there are test cases for both of them. Now, this unfortunately does not always work. So the canonical test case where the sort of loose coupling does not work is computational hemodynamics, which is a problem involving rather elastic vessels where you have incompressible fluid going in. And so when you try to apply this kind of standard coupling loop, you see that you only get solution when you have very, very small relaxation factors. So let's say up to or down to maybe 0.01 or something ridiculous. So, and noteworthy here is that you need to solve the Navier-Stokes equation in arbitrary Lagrangian Eulerian formulation, and the sort of moving mesh is solved by a sort of third solver, which is the mesh deformation solver. So this would be the sort of standard loosely coupled scheme. But as said, it has problems here. And why does it have problems? Well, the main problem is that we have a monolithic Navier-Stokes equation. And then when we try to enforce some inlet boundary condition here, for instance, incoming velocity, and we, while we are solving for the Navier-Stokes equation, the solid is basically fixed. So the first time step, we have this kind of case where you have all fixed boundaries and just incoming velocity. And if you can look at the equation of the incompressibly constraint and realize that this can only be filled if you basically have infinite pressure, meaning that you basically you cannot have a solution for this because you have incoming net flux to a closed domain. So this fails, but it turns out that we can actually make just a tiny, tiny modification to the continuity equation. So we add something called artificial compressibility, where now this artificial compressibility is not sort of a constant, but it's something that we can compute from the actual case. So basically, the artificial compressibility mimics the elastic behavior of the sort of structure. So when we put in a pressure and have tuned this correctly, actually we don't have to tune it, we can compute it, then the pressure caused by the sort of net flux coming in is actually quite closely the pressure that would be if we would solve this as a strongly coupled system. So when we apply this kind of simple method to the computational hemodynamic case, you can see that the convergence is monotonic and it's very fast. So you need 7 or 8 iterations for one time step, whereas here you needed maybe 70 iterations for one time step. And so you can see that with a simple trick, you win, let's say, a factor of 10. And well, we did some animation for this also, but unfortunately, time has not been very friendly for this animation. And here is another case. This is more like a test case. So we have a sort of a ventilation that we can get some fluid in, and then we enforce some rotational fluid here, and we can see that we get nice convergence for this kind of internal flow case. Now, unfortunately, there are cases where even this trick does not work. For instance, this well-known test case of Stefan Turek. So he proposed this kind of case, and all researchers in FSI, they bring me this case, and then I must say that unfortunately this artificial compressibility does not solve this, because it's not a closed, let's say, geometry. Well, there is a flexible sort of beam here, which then sort of follows the vortices caused by this sphere in front. So this is a case which really needs strong coupling, and there are codes that are sort of specialized in solving that kind of equations. So if this is your FSI problem, then Elmer might not be suitable for that. But there are other strongly coupled problems which can also be solved. For instance, let's take strongly coupled problems in harmonic fluid structure interaction. So we can solve equations, linear equations, mostly stemming from acoustics, and they can be coupled with plate, shell, or solid equation. For instance, we can take the Helmholtz equation and, for instance, plate equation. And then we can basically build a block matrix for these. So here would be the solid, and here would be the fluid. And these are the degrees of freedom related to the solid, and these are for the fluid. And basically you get this kind of matrix where these sort of coupling matrices then are sort of built by the library functionality of Elmer. So you get this kind of block matrix, which can be solved either as using block preconditioners or even as a fully monolithic system. Fully monolithic is needed if we want to solve eigenmodes. But this is a sort of nice framework, and it can be applied to different kinds of things. And here, for instance, we have tested for a strong FSI coupling in a case of a shoebox. So assume that you would have this kind of shoebox, and you would like tapping sort of the box, and you would see that, okay, if you are on a sea level in one bar, the lowest eigen frequency would be maybe, is it like 105 hertz, and when you go up to 0.1 bar, then actually the frequency changes by a few hertz. So basically you can solve these kind of problems that would be very, very difficult to solve having some loose coupled iteration. You can solve these as well with this kind of strong coupling on the matrix level. So here is a elastic plate going up and down, and here is the Helmholtz equation that sort of resists it's going up and down. So the higher the pressure, of course, then the sort of more rigid the system becomes. So to summarize, again, this is the hierarchical coupling, this is the loose coupling, and this is the tight coupling. So I made this slide many, many years ago, and sometimes I've been a little bit embarrassed to show it, but I thought that it's maybe suitable for this occasion again. And there are tricks how to improve that kind of loose coupling. And this is sort of one way, so you can exchange additional information between the models. So not just like go from one model to the next model, but this artificial compressibility basically changes a little bit of information between the models so that the models sort of converge faster with this additional information. And also we have in some cases used this kind of on-the-fly model lumping. So basically make lumped models and then tune the amplitude such that the sort of some residual is minimized on the coupled system level. And I don't have an example here, but basically there are modifications of the iteration method. So you don't always need to go to fully coupled methods. I continue with some examples. So here is a fresh example. This is a lithium-ion battery. It's a multiscale problem. So you have basically you have electrolyte. So where you have moving of free charges. So lithium ions go back and forth between the anode and cathode, and you have a Poisson equation for the electrostatics and the transport equation for the concentrations. The same actually for the solid states or the solid phase. So the solid phase is associated to each of these solid spheres. Actually, they are just micrometers in size, and you have many of them. So really, really many of them. And in each sphere, you should basically have a 1D model in spherical symmetry. So which basically makes this system a multiscale problem. So you have a macro scale in order of millimeters or centimeters, and then you have a microscale, which is in order of maybe tens of micrometers. And both have two different equations. So you have basically 4 different equations that are coupled. And this is actually quite a computationally costly problem, because in each node of the macro scale, you have a microscale finite element mesh embedded. So, and to make things worse, the two potentials, these that are associated to the electrostatics of the electrolyte and the solid phase, these are associated with the hideously nonlinear Butler-Volmer equation, which is of this type, and you can see that you have some potential equation here, which well, pretty much, well, makes any hope of sort of having some kind of simplifications or sort of unfeasible. So it's well, also the fact that in each node we have hidden a sort of 1D problem, which basically each 1D problem is individual. So really we cannot solve these problems at the same time. So the iteration method is the only realistic method to implement. And actually for this kind of case, even with Newton's linearization of this hideously nonlinear Butler-Volmer equation, you need easily hundreds of iterations. And this is not the peculiarity of Elmer, but also in implementations in literature, you find this. So here is an example. We pretty much can sort of reproduce some experimental results. And this is fresh out on Friday. It's chapter 69 under experimental models of Elmer. So, and there is a test case battery discharge. So if you want to save the world by modeling batteries, then here is a chance to do that. Coupling of finite elements and particles. So this is also a sort of coupling that you might want to do. So it's basically an example of heterogeneous models. So you have different models being coupled. And finite elements has its strengths, which are related to, for instance, genericity in geometry. And they excel, for instance, for elliptic equations. But for instance, pure transport problems are more challenging. Of course, particle-based methods, they have their own sort of strengths. And one is, for instance, that equations are written in the coordinate of the moving particle. And this means that in that frame, there is no diffusion of any kind. So this may be a nice method to sort of complement the sort of feature set of finite element methods. So, and of course, you may need some back and forth coupling between the two methods. The particle tracker of Elmer is not very cheap because it follows the particles in an unstructured mesh. So basically, we need to have topological information on the mesh, and we know, okay, if my particle goes over a face, into which element does it appear in? And this is quite economical if we take short steps, but not so economical if we take longer steps. So this is not sort of competing with other particle codes, but it's sort of nice method if you take short steps with the particles and don't have sort of excess amount of particles. So here is an example of hierarchical coupling. So there is a solver called ParticleAdvector and many test cases for that. Also, here is one of those, a little bit modified. So we have an incoming profile. I have a sinusoidal profile that comes in, and we have velocity going into this diffuser. And you can see that the sort of value is very accurately sort of transported here to the outflow. So this ParticleAdvector, what it does, it basically looks at each node and sends sort of particles backward in time until they meet the sort of origin where they then read their value. And this kind of technique, it does not introduce any diffusion, and it may be nice to sort of use this kind of solver to sort of study some advection type of phenomena, like you could advect even time or other passive scalars. So here is an example of the Navier-Stokes glacier by Thomas and company. So we applied this to that case, and you can follow the flow and like inherit, for instance, from the place the particle started. For instance, you can find the distance traveled. You can find what was the initial height where the particle started, etc. So this may be very interesting if you have a steady state case of a glacier and you want to know where the heck did this this piece of ice come from? And of course, this is just one example, but this sort of solver can be used to many other types of problems as well. There is also the possibility to have bidirectional coupling involving particles. So the particle dynamics can do this. So it knows how the fields in the mesh can affect the particles. For instance, the particle knows its position in the mesh, and you can, in that exact position, you can estimate any field using the basis functions. So it's not just a constant value in that element, but it's really approximated using the basis functions. So you can compute forces, for instance, to electrostatic or magnetic forces or fields, and you can compute viscous drag, etc. And also the particles can contribute to material properties or source terms of the partial differential equations. So for instance, you could have carriers of property. So if you have several types of particles, you can carry some property with them, and then you can see, okay, what's my fraction of my particle A of all particles, and then depend on the property based on the particle fractions. Or the particles may be sources for electric charge, heat, or whatever. So, and the contribution is not sort of just given to the closest node, but it's given to sort of all the nodes that are in the element where the particle resides. So there are many names for this kind of methods. So particle in cell, for instance, or material point method, etc. So I think it's not so well sort of settled field as, for instance, the finite element field. So here is an example of self-consistent Poisson equation. So we have an equation where we have fixed sources. So this is a charge density, fixed charge density, and then we have moving charge density. So this is associated to the moving particles, which obey the Newton's laws. And you basically can first solve the Poisson equation for electrostatics, compute the forces affecting on the particles, and then compute the new positions for the particles, and then their contribution to the Poisson equation on the right-hand side, etc. So, and continue this until this is consistent. So here is an example where I initially had background charge density of -1, and I know that these particles should sort of go and cancel the -1 with their total +1 charge. So, and indeed they go there. It must be said that, I mean, the physicists, they have their own sort of codes that are dedicated to this kind of problems. So this is more like a sort of demonstration. And here is another kind of demonstration of the particle dynamics. So here we have two types of particles. Particle A is this square here, the smaller square, and it has a little bit smaller, I think these are wrong way around. It should have a little bit higher density. And it basically goes down in this lower density fluid that surrounds it. And you can see that when you follow the particles, this is now the particle fraction, you can get features that you could not get simply with the finite element solution, because you have these tails, for instance, that would diffuse away if you would have the same number of finite element cells that you have now particles. So there are some fields where this can be of interest. So here actually you see the particles. I didn't plot the other particles, but of course you have the other particle type surrounding here. But there are problems. For instance, one problem is that these particles will eventually not be uniformly distributed. So you get this kind of places where you don't have much particles, and then the you cannot so accurately estimate the material properties of the particles. So again, here we can basically demonstrate nice sort of coupling. But if you have tons of particles, then there are dedicated codes that follow these particles sort of in a more economical way. But Elmer particle features, they are good if you sort of have particles in the same number as you would have, for instance, Gaussian integration points. If you have you need so many particles that their statistical sort of noise is vanishing, then maybe some other codes do you a better job. Finally, I have an example of magnetic levitation. So this was a case that came up on the forum some weeks ago. I followed it a little bit, and then I thought that, okay, maybe I try to solve it before this webinar, so we get a nice case for the webinar. But actually, it wasn't so easy a case. So this is a problem where you involve Maxwell's equations, Navier-Stokes equations, a free surface, and a mesh deformation. And you try to find a sort of convergent solution for this. And this test case was suggested by Roland Ernst on the discussion forum, so you can find some discussion on the EM levitation topic in the Elmer discussion forum. So in principle, we have all the needed features. So we have here a ball, and then we have some inductors in different directions. So basically, we have current density that generates a magnetic field, and the magnetic field generates currents in the liquid metal, and the currents then they meet the electromagnetic forces and make the sphere levitate. The parameter space is pretty challenging, so these are preliminary results with easier sort of parameters. So even though we knew that, okay, this is a little bit tuned so that the gravity and the electromagnetic forces, they are on the same sort of roughly on the right ballpark, but even then the sort of initial transients are rather demanding, because you need to have a very, very small time steps in order to capture these sort of initial phenomena here. So this is also very much conditionally stable. So you need to have here a very small time step. And in this kind of case where you have mesh deformation, if you end up having sort of too much deformation, then the mesh will be so much deformed that you cannot compute with anything with that anymore. So that's the one challenge. So luckily, there is a nice solution for this. So you can couple Elmer with OpenFOAM. Juris Wentzels has created a nice Elmer OpenFOAM library that combines these two codes in a very nice way. And OpenFOAM has some Eulerian methods that are more robust for this kind of coupled problems. Okay, some maybe a little bit comparison between our experiences in loose and tight coupling. So we mainly use these loose coupling or segregated or weak coupling methods. Unfortunately, if you have a very strong coupling, strong physical coupling, these do not always converge. The plus side is that it's very easy to utilize existing solvers for individual problems. So you can just take out of the box the different solvers, and in Elmer you have features that enable you to couple them sort of out of box. You don't usually need to code or even anything on the interfaces, etc. And you don't need to estimate the difficult, for instance, coupling terms or whatever. And the resulting individual matrices, they are more easily solved by optimal methods. For instance, if you have Poisson equations coupled, then you can use multiphysics methods for the individual methods, etc. And these are using memory more efficiently. Then, on the other hand, you have tightly coupled methods, or monolithic, or whatever name you want to use it. They are more robust in the whole parameter space. The reuse of existing solvers is often a little bit more difficult. You have to estimate somehow the coupling in order to sort of take use of the strong coupling methods. And the resulting monolithic matrices may be ill-conditioned, or let's say be quite difficult to solve, limiting the choice of linear solvers. And often these consume a lot of memory. So there are some possibilities to combine the sort of merits of both these weak and strong coupling schemes. So we would, of course, like to have the robust convergence of the couple problems, but still use optimal linear solvers and reuse the individual solvers and have rather efficient memory use. And there are indeed some strategies that help to sort of gain all these together. So, for instance, we have been using the artificial compressibility in FSI, so making some tricks on the continuous level, or then doing some tricks on the discrete level, so we can play with the matrices and, for instance, introduce block preconditioning techniques, etc. Okay, I think this was what I had in mind for today. So if you are interested in Elmer, here you have some links, and now I'm happy to take questions if there would be any.
Thanks, Peter. I don't see any questions at the moment. So if you want to speak up, please raise your hand, or it's not too late to type some question into the Q&A. Kaspar wants to ask, I switch you free. I unmute you. Can you try?
Yes. Can you hear me?
Yes, perfect.
Yes.
Yeah, yes. Thanks, Peter, for the great presentation. I would like to ask about maybe a different aspects, which is also kind of related to coupling. It's about phase change. Yeah, I mean, it's a kind of coupling between a solid phase and a liquid phase when you have a moving boundary in between. So maybe you can give a comment. How do you see the current capabilities in Elmer in this regard, and what are maybe some future developments which you have thought about so far?
Yeah, so it's a little bit time since I last used different methods. I think the methods are, especially for your field, they are sort of quite sort of usable already. It's just that it may be difficult to sort of know which of them to use, and I think, yeah, I mean, may I ask what kind of sort of challenges have you had?
Yes, I think the last challenge which we discussed, I think a few months or last year was it, I think, was about a transient phase change where you have a moving boundary between a solid and liquid phase. And you calculate this in an unsteady way with a moving mesh. Yeah, so this was not so easy to solve. So
yes. Yes, I think the one challenge is I guess in crystal growth is the different scales. So if you have unsteady flow, you end up having so small time steps, maybe less than 1 second.
Yeah.
And if you have this small time steps, then having this sort of computing the heat fluxes and then taking the sort of growth speed from there, basically I think it could work, but then you end up having to spend like thousands of time steps to sort of evolve the geometry.
Yes.
Then you may, of course, want to speed up, but then I think you may end up having sort of convergence issues. So So yeah, I don't have a sort of, I think you pretty much know where we are currently. And of course, the sort of, well, it's a challenging field if you have a unsteady sort of very also like violent sort of type of flow phenomena involved. So I don't, maybe we should look at this together. So
yeah, maybe it could be a more detailed discussion sometime later. Okay.
Yes.
Okay, thank you for your comment.
No. Any other questions?
I don't see anything coming up.
I can add one more question if I may.
Yep,
yes,
sure.
Please.
It's about free surface. So you showed this last example about levitation, where I think also the free surface of this liquid metal, I assume, was also calculated.
Yes,
right?
yes.
And this was also done in Elmer, considering the electromagnetic forces.
Yes, that's true.
Okay, so can you tell more about this model? Was it a 3D model for the free surface shape, or what are the limitations of this model?
Yes, so this one. Okay, so what we see here is on the right-hand side, this is the velocity field, and on the left-hand side, I think this is the magnetic field density. So just to give a better idea of what is going on here. So these are the coils that introduced then the magnetic field, and this is the current density.
Okay.
Well, the challenge here was that our free surface solver that, for instance, Thomas knows very well, which has been mainly applied to crystal growth and then later to computational glaciology. It assumes that it is mappable to sort of to a plane, or to, like, if it's 2D, that you have a principal direction that so for instance, in this case, it would be only a function of x.
Yes.
And in 3D, it would be only function of x and y, and you would compute the height. The problem in this case is that we cannot use that because it is not capable of dealing with the local coordinate system. So what we did here is we compute there are two forces affecting on this bubble, the gravity and then the electromagnetic forces, and then they give, for the Navier-Stokes equation, of course, a suggested flow field. We don't apply any boundary conditions on the boundaries, so the boundaries are sort of have just natural boundary conditions. And of course, this then introduces some velocity on the boundaries, and as you see here, and we use a tailored version of the normal solver, which actually the modifications is in the open source already, so that we project only the normal component of this suggested displacement and move this mesh then in the normal direction only. So because I know here could be some convection rows. So if we would be taking the suggested sort of velocities and using them directly to displace the mesh, then I feared it would sort of rather quickly sort of distort the mesh. But the idea is that we only change the mesh in the normal direction.
Okay, but this free surface calculation is axisymmetric. It's 2D, or
in this case it's axisymmetric, yes.
But the model is also capable of a 3D shape.
Yes, basically it is. I just was doing it this week and testing the parameter space, etc. It would take so much time that I didn't have time to go 3D. But I think it would be solvable in 3D, just not sort of within a day or two. So because all the equations are also available in 3D. So that would be, if you are interested, that could be done. But on the other hand, I think that the nice coupling between Elmer and OpenFOAM by the Elmer OpenFOAM libraries is more robust because that has a sort of Eulerian description for the fluid.
Okay, but in principle, this kind of levitation problem can be solved poorly in Elmer and also using the coupling. I mean, you have two solutions which are possible here. Yes,
basically, and this would be sort of probably for more sort of civilized problems and yeah.
Okay, yeah, thank you very much.
I don't see any further questions. May I ask a question concerning to that slide you have on now? So is it possible to include also surface tension to that problem?
Surface tension is there.
Is there already?
Yeah,
okay.
Yeah.
Sorry that I missed.
Yeah, I didn't probably say that even. So there is surface tension, but it seems that, well, actually, I don't know how much it affects the system, but I think it helps to sort of settle the because this looks like rather sort of nice spherical. So I think that it has significant effect on the solution. Okay, if there are no further questions, then I think this is the end. I hope you all a very nice Christmas and maybe we see next year. And if you have some questions, please, you can email me, but if it's of generic nature, then please ask it on the forum. But of course, also private mails are welcome if you have some sort of strategic collaboration or whatever type of issues. Bye-bye.